We'll get started. So thank you all for coming, and also to people tuning in today. I'm Stan Pennington. I'm a program manager in the Windows Multimedia Platform team. We provide audio-video infrastructure that underlies a number of Microsoft solutions and also third-party technologies. So let's go on to the agenda here. So my cohorts have given several presentations. There's so many good presentations and obviously so much to take in. But my friends that I work with have given talks 775 through 778 as really sort of a core lead-in to this level, which is, of course, a 400 deep dive. And so I'm going to address why would you want to do extensions on what we provide in the box. And if I can, there, it just responds slowly. And then we're going to go in. There's a lot of breadth and a lot of depth overall. And of course, I'm not going to be able to convey just completely, expert knowledge. And being a program manager, they only have a certain amount of that. But I will convey what I can as far as some depth in one area, so you can really get a feel for it, the amount of effort, the technology that's involved. And then we will go in and see a little more of the breadth, but we have to be a bit more cursory about those levels with the limitations in time. And then finally, we'll wrap up on that. And what I would like you to get out of this is just a sense of how you go after this technology, and also give you a number of links in here that you can go back to for information later as you dig in deeper. So I'm going to address the why a little bit more. As I mentioned, the talk 775 through 778 really concentrate on consuming our technology. A lot of that is completely integrated, where all you have to do is use an audio or video tag and specify the source, and it plays. And so the components are all happening indirectly. We're taking care of the heavy lifting. So you're consuming those components. And that's really the main focus of the other talks this week that we have. Now, historically, when you go to the next level of wanting to do something custom, something we don't have, then you need to descend into the infrastructure. And of course, historically, our infrastructures have always been native C++. There are many reasons for that. I'm going to go into some of those. And here you'd be authoring components, because our goal is to be modular and extensible so that we can reuse these components in several different scenarios, whether it be playback, transcoding, sharing, and capture. So we want, every time we have a new component, we have to invest in the development and test. And so if we can reuse these components maximally, it is in our best interest and also, I think, helps out our customers. Now, historically, being that the infrastructure was all C++ COM, that meant that to consume it, at least some layer of an application where you want to spend your time and effort to really differentiate would have to also be C++ with COM, maybe your entire application. So quite a bit of investment there. And there have been efforts over the years with nascent efforts to try to have wrappers that would work in specific scenarios. We have even an effort by one of our MVPs, a great effort, to make a wrapper for our technologies, our infrastructures, into higher level languages. But usually what you'll run into is that interoperability, I'm not just talking managed, but just general interoperability across technologies, because our audio-video pipeline is really for audio and video. There's a distinct set of technologies for image processing that there's a separate talk on that, a great talk about Cool 3D FX that's in the related sessions at the end. So imaging has its own effects pipeline, and that makes sense to us. And then finally, there's the levels of DirectX that can be used. And so a certain amount of interoperability is very important to have, but sometimes difficult to achieve. So that's the historic sense that I tried to paint. And with Windows 8, with the Windows runtime in between as both an abstraction and also as runtime support, we finally have something that rationalizes and makes it so you can have these infrastructure components as native C++, be able to consume them then with the language of your choice much more easily, and be able to put that effort into really making your apps better rather than having to concentrate on a lot of low-level details. So that's really what we're trying to get across. Now, since I'm going into this 400 level, we really can't get very far with further discussions unless we talk about something, this is kind of my diatribe, about media formats. So when you're working at a level of just wanting to play a file, transcode a file, using the APIs from consumption, then pretty much you just have to know the file extension, maybe the MIME type or the URL, and whether it be a local file or coming from some other place, it's all pretty much handled. But once we descend to this level, since the infrastructure is modular and extensible, it also turns out it's very important to understand it maps to the representation, the actual way that media files are implemented. And here, what we get into, of course, is that they have a certain structure of metadata, headers, and sometimes that can be incredibly complex. And then you can have 0 or more video streams, and same thing with audio streams. In fact, you might have mutually exclusive audio streams that can be selected for things like different languages. And actually, Daniel Schneider's talk, 776, I think it is, showed that off in a sample. So we have then also the possibility of ancillary streams. I didn't show that, but you could have private streams for various purposes. And then what has to happen to be able to handle this in a modular and extensible way is that you need to know the proper components that handle each of these things. And so for the header, the metadata, that's usually that you have to parse the container format. And this is, of course, where you get into somebody says, you have like a customer says, I have an AVI file, and it doesn't play. Okay, there are probably 100 permutations of different codecs that could be used for video and audio within that AVI container. And that's really the root of the difficulty of why it may play in one configuration, it may not in another. And that will lead into some of the aspects of what we've done with Windows 8 for audio-video around really embracing the Apex model, is that instead of the classic COM, elevation, installation model, and instantiation that you would have with codecs historically, we have the model where you bundle that codec with the Apex, and that way it's insulated from other apps. So you would have at the container level your parser if you're actually consuming it, your multiplexer if you're creating it, and then video and audio codecs. Okay, so this is a little dense. I will walk through it. So it turns out that if you're going to do extensions, you kind of want to get a sense of what can I do. And this is really geared toward the MetroStyle environment, this information here. It turns out that since some of the other talks I talked about, we're leveraging the Media Foundation technology underneath all this. The Media Foundation is very extensible. That's the story we've had for a very long time. And really, in Media Foundation, if you're using programming to the traditional layer of the media session, you can get control of the topology. You can insert, modify any component you want, anywhere from media sources, transform sinks, and just pretty much have arbitrary capabilities. When we get into the MetroStyle model, we have to start talking about controlled extensibility. And this gets into the fact that the MetroStyle UI is having to go through and provide richness in the presentation. So when you talk, for example, JavaScript and HTML, there is a rich compositor, the core of Internet Explorer, running to do that composition and presentation. which is unlike the case of traditional desktop apps where you pretty much just have the desktop window manager as the only compositor in the loop. Here you have an in-app compositor. Very similar situation with XAML and C# or C++, where there's a rich compositor, and much like WPF and Silverlight's compositor, that's bringing these things together. So if you were to go in and put arbitrary syncs and other components in, you might be able to actually cause problems with the intentions of that immersive UI. So this has to be controlled to some degree. So we'll step into this a little bit. One of the first things to note, as I said, playback, capture, transcode, and sharing does not show up here. And there's a very good reason for that, and that is the model for sharing is that the extensibility happens in somewhat of a different way generally. Sharing is all about a contract, as you may have heard if you attended the other session about Play2. Play2 is the binding. That's where you see media sharing. And Play2, what will happen is, being that it's a contract, then when you use our implementation, you're going to get certain functionality that makes sense and works best for the type of devices that we support in box. If you want to provide support for some other transport, for some other kinds of devices, then it is possible to implement your own Play2 contract and be able to access that via the contract mechanism. So it won't show up here. But the things that we can do, if we have an uncompressed video and audio stream, and here I have to note, let's say cases happen where you want to capture, let's say you have a webcam and you're capturing some content, and you say, I want to modify that while I'm at it. It came in let's say it came in with one codec, or it's in some raw Bayer format or something, and I need to convert it. And then you go ahead and insert your component, and you say, wow, the CPU usage is really high. And the reality is, of course, is if you're going to do modifications of an elementary stream, video or audio, then the only way you're going to be able to do that is if you decode it first, run your operation, and then re-encode it. It actually may be the decode and re-encode is what you're trying to achieve. You may be trying to resize. You may be color space converting. You could be doing all sorts of things. So this is really trying to just capture that within these three areas, that if you wanted to be able to access the uncompressed streams and do something with them, this is really what we call an effect or a processor. That's if we're getting down to our own lexicon for within the media platform team. So things you can do, obviously you can, I'm not going to hit every one of these, but you can modify. For example, let's say you have a video stream. You can go in and change each one of the pixels. You can do neighborhood operations like a convolution kernel. You could do, for example, in playback or capture, you could be doing image stabilization. We actually provide that in the box as an effect. So usually you won't have to do that yourself. You can leverage ours if you like it. If you don't like it, of course, you can make your own. Even in transcoding is the possibility of doing stabilization. And for each one of these, there will be a mechanism by which you can have these inserted into the Metro-style underlying pipeline. But you have to understand that it's indirect. You do not get access to the media session topology at that level because it would be too easy to get to configurations that could be problematic with the level of integration that we're providing. And I'll go into a little more about that later. So, of course, one of the other things, we're actually going to show a demo on this where you could just be analyzing, not even modifying those streams that are coming through. And you could be working with data that isn't even audio-video. You might have some kind of metadata stream you want to work with. And finally, to mention, we've had some other slight discussions about content protection, that the model here for an effect is very good for being able to decrypt and encrypt elementary streams. It's part of our standard model that involves the Media Foundation Protected Media Path. So then when we move to doing something more than just handling a raw elementary stream, we might want to do something over the wire. So let's say we provide certain protocol support in the box, and you want to do something else. You want to talk in some other way, or you have some specific kind of device you want to interact with. In this case, there is another model that has to do with our Media Foundation media sources and syncs, and these have an aspect that is for transport. And so some of the things you might do, you can implement your own adaptive streaming. You could have completely unique I/O. but mainly what we require is that type of I/O should be AV stream, which is within the kernel streaming model that we have, in order to best interoperate with our system. That's what the webcam capture does today. Now here you can see I put sharing back in the table, and it's because we're talking about formats. And here's where this is really the most advanced type of extensibility, is where you're actually going to support or implement support for a container and possibly codecs that we don't have in the box. And I'll go into more about that later, but you can see a matrix here of what you should expect to be able to do in terms of, can I use it for input? Can I use it for output? And in some cases like sharing, for example, when it's using our contract and our implementation, you'll be able to use it on input because of the way that media sources are resolved into the system, the actual source resolver in Media Foundation, but you won't be able to use those on output with our implementation, and that's rational given the integration with the types of devices that we have to work with. And also, of course, codecs. I think a lot of people are familiar with those, but you can also work with, again, ancillary streams. So to give you some ideas here, just specific ideas, run through things that you could do that would be of value with your own extension. So for an effect, more generally we call an effect a transform. You could say, I'm on a bus with my new slate, and I don't want to have to be going back and forth to the overall settings to be able to change, let's say, the display brightness and contrast or other characteristics. I'm watching a video, and the desktop's fine, but I really want the video because there's some certain amount of sunlight on the bus and everything else. I want to be able to control that in-app. And so I can use an effect to do that. And I could make it so I can wire it up through Windows Runtime. This is the key value of Windows Runtime, is it provides a standardized convention by which you can interact in those higher level languages with that component, both for configuration and for events and even other things you might be able to think about. There are certain limitations there. We can go into that a little bit later. Also, for example, I'm on that bus and I'm listening to audio. And what I find is that across a number of pieces of content, the volume's all over the place. And I want to implement a normalization algorithm. I want to go through and do some compression and limiting, whatever I feel like. I can make that experience better for the user when they're in that environment. Another idea is you may not like or may not want to use the kind of algorithms we have for resizing, and you want to do your own, just totally unique modifications, your own DSP. You can do that. And then finally, and this is something we're going to show here with our demo, is being able to just process captured streams. And actually, we're going to concentrate on video. I don't mean to be giving audio short shrift, but my sub-team concentrates on video mostly. We've had some other talks that have really dug into audio. So I'm not trying to slight it at all. They're both equally important, of course. And so once you pass the transform level, which is the easiest one, and go to the idea of bringing in a transport, so you're bringing in something from outside the PC usually, or it even could be local I/O that's something custom. Here, the media source is the type of component you have to work with, as I was saying, just to sort of reinforce these various roles for the extensibility. And here's where, like for example, you have some adaptive streaming protocol that's very popular that you want to support. This could be done here. And, sorry, go back for a minute. When I say in friends, a media source usually isn't explicitly selected. There's an indirect relationship, of course, that you encounter a piece of content that may have a file extension or a MIME type or a URL, a protocol, and we do that mapping. So there's some other pieces that we're going to get into that show you how you actually map to make that media source indirectly get selected for the type of content. And then finally, if you wanted to go all out and provide support for a new format, you would be working with a source and sync, and then some of the same components on the source resolution side. And finally, you would have likely transforms for doing your codecs. So here you might have a completely new media format that you want to support. So now we're going to go to a demo, and if you had attended Daniel's 776 session, we are going to show the same demo So we think it's quite fun. So are you ready to?
Sure.
And just.
Should we go?
I will crush you. Oops. Uh-oh. I actually haven't run
Can we
this.
get audio on this guy? Bad collision detection.
Blah, ha, 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 ha. Hey, where's the bonus round where it goes boop, 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 boop? Okay. Oh, man. Okay, I'm terrible. I'm going to stop. I hadn't practiced at this, sorry to say. Okay, so thank you, Daniel. And what we're going to go into next is to show how did we build this. Now, I do have to apologize that we're showing this to people, and we don't actually have it as part of our sample collateral right now. But we felt that, and this is really a logistics issue, that we put this together to be somewhat more interesting than some of the typical samples that we have, and that we didn't get it into the payload. We are assessing whether we want to provide it as is or make modifications. But I'm actually going to show you the code here and walk through it so you can get a sense of what we've done and see how approachable it is. Oops, sorry. Slipped into the wrong thing. Excuse me. Okay, so first of all, what you need to know, I'm going to switch back for a minute because I need to give you a little more background first. If we're going to look into code, we have to have an idea of what we're looking for. Actually, I think I'll wait on that. I was going to give that to you now. I think I'd like better to just cement a few ideas more before we go to that. So we'll get back to it. Okay, so let's just talk just a bit more about what we're doing with this extensibility model. And that is, you get to implement this once, of course, in just one language. And then the other part of it is, since I mentioned this Media Foundation, these components are very well formed already on MSDN. There are vendors who have implemented these things all the way from Vista up, and we've maintained that model overall. We've done some specific enhancements that involve both desktop and the Metro style, and I'll get into those to some degree. And then finally, not finally yet, getting there, with the runtime, as I mentioned, the Windows runtime, you can be able to use these from whichever language that you desire. And so a few other points to make about this integration. As I said, Windows runtime makes it so that we can have a much greater level of interoperability. DirectX 11, we embraced in Metro style DX11, whereas video historically in desktop has been on DX9. With DX11, you get a greater capability to work with shaders, with Direct2D, with all of our other goodness that has been invested in for Windows 8. Another thing that's interesting is audio offload. If you remember back, if you've been involved in this at all, remember back to the Vista timeframe and Win 7, there really wasn't an opportunity for any kind of hardware offload for audio. It was always being done in CPU. And in Windows 8, there is that capability, and it's mainly meant to increase efficiency. And for that, the compressed stream is provided through. There won't be a codec in the topology. It's provided through directly to the sync, and that goes down to the driver and hardware, and they take over the decoding. And then, of course, you have cases where you might want to do general-purpose GPU. You might be using completely proprietary APIs from some vendor or some other abstraction that you want. It might be in C, it might be in another language. Of course, since the component is native C++, you'll have to work in a way compatible with that. But you can connect into arbitrary processing APIs through this. And then finally, that we have, as I mentioned, this is the whole Apex promise, that these components that you deploy don't get into the interaction with other applications. They're completely bundled, deployed, installed, run in the scope of your app. So what this means, of course, and I think we covered this to a fairly good degree, is that the basic pipeline, because it's doing a lot of heavy lifting, if you're running HD video, maybe multiple streams, and you're trying to touch every pixel, and you do that in JavaScript, you're easily going to take hundreds of milliseconds often. You can do some really interesting tricks with trying to have pre-calculated tables, doing loop unrolling, all sorts of crazy things, but in the end, you'll probably end up with fairly unmaintainable code. And also, you're going to get hit sometimes with overhead of things that are happening to you. Similarly, with C#, effectively the managed DirectX effort showed that you can hit often 95% of the performance of C++, but at certain times, you're going to get hit with garbage collection and other things. And if you get behind on these soft real-time deadlines that you need for media enough times, you're going to glitch or you're going to have other problems. So we need to maintain this as native C++ at the lowest levels. It also makes sure that we don't run across interop boundaries with components and other kind of strange things that go on. And so, of course, so really at the core of this, our components are, as they've always been for Vista and Windows 7 for Media Foundation, they are really classic COM implementations. But what is different is that they can't be installed global to the machine. They can't be instantiated in the old COM way. They have to be made activatable. Basically the runtime class that is activatable. There's a lot of documentation coming out on that from just the general Windows runtime collateral that you have here. So I'm not going to belabor that at all. I'm going to talk about, when we go into more detail, I'm going to talk about the specifics of things that are relevant to the audio-video aspects. And then I kind of go on over this already, but we still have even that you can usually achieve the best efficiency in C++, and also hardware that, if you did something in a higher level language, you'd have to write some wrapper to be able to talk to arbitrary hardware. You don't have to do that here. And just to cement the way this layering works is at the top level, of course, you have your app, and then we have that abstraction of the Windows runtime. Do note here that the audio and video tags don't run through the Windows runtime. This actually makes sense, is that the tags are really a specific implementation of specific for playback. And so it makes sense to expose the functionality directly on those tag implementation as either fully standards compliant cases or proprietary extensions where absolutely necessary, so that you can interact with that tag in a very natural way. Similarly, but not shown here just due to complexity, is when you're working with the XAML media element, it will be the same kind of thing. The media element is a custom wiring of the underlying technology up to the application. And at the next level down, we have all of our investments that are really the key integration into MetroStyle. These are things that are above the media session level. I didn't actually show the media session here. I wanted to keep with the very standard picture that we have across all of our collateral. But there is the investment in playback and capture across the board as you go across that layer. And then at the red level is all the components that I've been talking about. And they actually do use, pretty much across the board, the media session API under the covers. It's just being done as part of our implementation. And then finally, at the lowest levels, we're integrating into DirectX and also AudioStack. So there are some alternatives. There are cases where, because this is a high level of integration, we're trying to make it easier for, say, the 80% case of use. There will be times when you may have a specific need that can't be done within this model, and you will need to deviate from that. The media session is always there for desktop, can be used. And then in MetroStyle, there are certain options with trying to make use of the very lowest level of C++, where another intermediate component below that playback preview, that third layer, is a C++ element called the Media Engine. That's part of our implementations. It's actually exposed to you. It's basically a super frame server. You can make use of it to directly provide you with video streams, and it actually steers the audio to the stack directly. But the video streams are available to you for further operations. And so, try not to make the diagram too complex to wade through. But if we had to boil this whole section down to this point, into one little catchphrase is that you only have to write in native code these key pieces at the bottom, and then with this integration, you'll be able to leverage it broadly and much more simply than we ever have before. So now I'm going to go back. Decided to kind of take it in a little different sequence. I'm going to go back and talk about what we saw in that demo of the game. And so effectively, whoop, I got ahead of myself. So what we do is that we have, of course, that game is in JavaScript and HTML, and we're basically just using a canvas to be able to display the video captured from the camera. And then what will happen, the camera's shown down at the left, of course, and we're going to overlay scalable vector graphics using HTML on top of that so that we can effectively have an overlay for our graphics and play the game. And then the flow underneath, though, of course, is going to be that the video frames come in from the camera, and they really just pass through to that canvas. So it's just capture preview. And then we're going to be extracting the coordinates and putting them into, sending them upward to some JavaScript code, and then providing that over to be able to control the actual UI interaction. So before we go any farther, I do have to give you a little more information about these component models so that when we look at the code, we can understand, what it is. Otherwise, it would just look like, just a mass of code. Is that the effect, as I said, is a specific case of a transform. And here it is our standard, well-documented MFT model, Media Foundation Transform, which is usually for an effect is one input, one output, but can actually sprout multiple inputs or outputs, and also has capability. The basic MFT is synchronous, which is the easiest thing to do and the best for software. But if you actually had hardware underneath this thing, a synchronous model where the pipeline is polling is not going to be the most efficient because you really can't know the cycle at which the hardware is going to be done with operations. So you can actually put this into an async model where it actually gives events on saying that it needs input and has input ready. But overall, if you're thinking of it, you say you have samples that flow in and samples that flow out. And usually the process input part that I'm showing on the left side arrow on the data flow is really mostly housekeeping, especially shown that way in our samples. And then process output's the part, if you were to go through and look at an MFT, process output's the place where you're going to say, here's where the meat of the operations on the effect are. And so all the rest of it in blue, the basic interface that this thing has is IMF transform, and there's certain basically configuration status things. But what's new, as you can see, just to reinforce, that there are custom interfaces that have to derive from MyInspectable. You have to be able to activate this in the Windows runtime way. And those are quite simple, so you can effectively just make a hybrid. So if you made one of these effects, you could make it so that it works in Classic COM, if you're using it in desktop. And you could also use the same component in hybrid for Metro-style activation. But you can't cross over, of course. If you're making a Metro-style app, you can't have dependencies on desktop components that are installed outside of Windows. And there's some links here that I provided. I usually put the whole link in case, sometimes when you put hyperlinks as text, they can tend to get munged. And so I wanted to make sure that people can try to get back to them as easily as possible. And then the other thing that we want to know, and this is where we really descend to the lowest level that tends to require some skill. But really, if you get into this a little bit, it's approachable. It's the idea of the representations of data that are efficient for the actual hardware flow and, well, for CPU and even like GPUs, that if you're going to be working with, let's say, video pixel data, then it would be nice if it was always in one representation. It was just, OK, it's always red, green, blue, and alpha, and it's always in this format, and we're all happy, and we only have to make one implementation. It's not the way it is. That's the reality of it. So these representations, what we do is we say when you have, like for an effect, you're basically handling uncompressed video. Then you're going to have an uncompressed frame, which is a sample, come in. You may actually aggregate several samples together and call that a buffer. So you can track it, but basically you have samples coming in and you have samples going out. And those samples have several potential representations. They can be just, sometimes they're linear in memory as one-dimensional. Other times they may be represented as two-dimensional. When they're two-dimensional, you have the additional issue that for efficiency in hardware, that usually there's this concept of stride that, okay, so let's say your video width is not an even multiple of, say, 16 or something, that you actually need to pad it out for best I/O to the hardware. If you don't do that, you're going to slow it down significantly. So stride is just this concept of, okay, let's say my video was only 700 pixels wide, but then the actual line of data that's in memory is longer on a 16-bit boundary. That's really it. So you just have to keep track of stride, or else your pointer is going to be off every time you access a lower frame, a lower line, and you're going to get your completely garbled up thing. Of course, also with video, you're going to have where the representation, some of you I'm sure have gotten into this, where historically, that for some things, like let's say you're processing video and you want to easily handle changing the brightness, well, a YUV format makes sense there. Is you're separating out the Luma component as one, let's say, a byte representation, and then you'll have a couple of chroma, of color components, and that's really good for certain kinds of video processing. In another case, especially when you get to the point of wanting to feed stuff into compositors, having RGB representations is best, and within that, there are several different types. So there's a number of common ones. I can like rattle off, YUY2, NV12, all these other things, and it can be off-putting. So what we really would want you to do is use our heavy lifting. We have some samples. We have some samples that go back to Win7 and Vista around MFT effects, and they show some helper functions of how to take as input, a given representation like YUY2, be able to do work on it, and then be able to output to whatever negotiated format is happening on the output. I should also mention here really quickly that if you're coming from the direct show world, primarily, I've talked to several people offline who have done a lot of investment in direct show, that at the core of this, these concepts are basically the same. The big difference between Media Foundation and direct show is that direct show is inherently a connection-based architecture. You have pins. They negotiate for connections. Those connections tend to be fairly static, and that there is the base class code that does a lot of things for you and hides a lot for you. It was an intentional effort in Media Foundation to not use base classes because they hide so much and sometimes can get to be rather unwieldy, but to actually have the code all be present and linear. It is quite possible, if you're working with these yourself, is that you could refactor, some of the boilerplate code into something that that is more amenable to you. You could also do things like, of course, try to convert inputs to always a common format, and then do common processing and go out. But you may run into efficiency issues. If you're doing color space conversions, can actually take a significant amount of CPU. So these are the kind of things that you just have to wrestle with to some degree when you're down at this level, and that's because you're so close to the hardware. And of course, Media Foundation has some conventions around media types. Well, actually, types are really just audio and video, but subtypes of these representations of how you be able to tag these buffers and samples and say, oh, I know what that format is, so I know how to be able to process it. And then Media Foundation, this is one of the other big differences between Direct Show and Media Foundation. When I said Direct Show is all connection-based, Media Foundation is connectionless at the streaming component level, and then there's a higher level control layer that does all the orchestration of how the samples flow. And that actually makes it so that the individual core components are simpler, lighter weight, that they can be changed on the fly much better. And one of the biggest things it gives us is that the threading models can be managed more effectively. So like in Direct Show, what you usually have is you'll have threads that are embedded, and they're running, they're running inside, and you have no control over their thread priority. But what we do in Media Foundation is we have the idea of work queues and generally not embedded threads. So you queue work up. There's an asynchronous model in Media Foundation that takes care of this. There's a convention that's very similar to the kind of async model that you've seen here for Windows Runtime. So you queue up work on a queue, and it does it for you, and then it finally gives you back a callback when it's done. So it'll feel fairly natural to use the MF async model here. Okay, so before I get to that, let me actually go into we'll go into a little bit of detail when you kind of see effectively sort of the layout of this thing. And so, as I mentioned, this isn't in the SDK right now, but it's useful for you to see. And so some of the things are really just helpers. There's the ability, some code to be able to help with callbacks, be able to manage that when you have a buffer of data, you've got to worry about you're accessing it contiguously. You don't want to be saying, I'm accessing over here and somebody just came to have the frame on me. So there's a little bit more of a helper there. There's the wiring into actually being able to fire an event. Because what this effect is doing is every time it does processing on a frame and gets a result where it says, hey, I saw a spot, it's going to actually fire an event through the Windows Runtime Model that the app can catch up in JavaScript. So really, at this level, we've got, then what happens is we break it apart a little bit in that with standard COM, let me actually get to the right level here. So with COM, what we'll have is there will be, of course, an IDLE file. You always have to have a contract, a COM contract around this thing. And as often is the case, this is just this is some code that was put together very quickly. But what you'll find as often is the case with low-level code is that the most important things are at the bottom. And so we basically have broken the problem apart into 3 runtime classes. One is the actual processor, the recognizer, and configuring it. You want to set it up with the initial parameters and such, and that's all done really through, basically WinRT configuration. And then you're going to have the actual object, so effectively the payload of what your event's going to be, upward, that says, okay, I found a spot, and its center is this, its size is this, and then the app can work on it. And then finally some wiring that has to do with just handling the event itself. So that IDLE is the contract around things. And then we've broken apart the code itself into the pieces that do the actual processor, the recognizer, and the event just the event GUI, and then the handling of the object description. Let's look at that just for a second. So it's very simple, as we're just saying it has typical constructor, destructor, and then a separate initializer. And then we're going to go in and do an initialize to set it up to the default. So I mean, this is about as basic as it can be here. And then when we get into the meat, though, let's look at how this recognizer works for just a sec. So here what's going to happen, of course, is you're going to have to set your initial values on the thing. But if we want to say, well, what matters, let's go back to that kind of the prep we did. And here we go. Okay, so we're going to go back to looking for process output. And, actually, excuse me, I got the configuration one. We actually want the transform. Excuse me, I clicked on the wrong thing. My apologies. So what we want to do is get to the I want to get the other one. So process output, here's where we go in, and we're going to be having potentially a loop that is just going to work on all the pixels in this thing. And we have actually broke it apart into some pieces. There's some other housekeeping that has to be done. But what we decided here to do is actually have it call another function, which is, typical when you're writing code to modularize it, of onProcessOutput. And that's going to go in and actually start mucking with these bits. And so here it's even been broken down further, where there's the detection of the object and finally the ability to mess with it. But so let's look for detect here. Sorry, I'm hitting the keypad on this, or the touchpad on this. So detect here, there's where you're finally getting down to the meat of it. So if you just step through a little bit, what you'll see is that we actually are doing, in the end of this, when you derive down far enough, you're just doing basically a loop that is processing all the pixels here at some point. And what's actually where we get down into this, so this final level here of the processor where you're going to be working with, there it is, finally. So if you go down enough, you'll find that there's just this XY loop where you're going to go through all the pixels, and you can do something. And this is a very simple algorithm. All we're really doing when we finally get down to it is that we are going to find the thresholds and find the edges of a spot. And then we're going to walk around those edges and try to determine that it's basically kind of a circle-like blob, to find the center, and then be able to actually provide that information back when we fire the event. So again, this is code, sorry, that's not available to you, but it at least shows the taxonomy of this thing. So it builds into a DLL, and it's a standard COM DLL with the addition of the piece that has to do with, with the Windows runtime. And that piece really is you use the middle tool to be able to take the IDLE and be able to process it into WinMD. And as you probably run across, the WinMD is the metadata that makes this thing exposed fully and understood at runtime up into the app level. So now we've kind of taken a look at this. So what you would do to build it, of course, is just to be able to create that WinMD, be able to build this into an actual DLL, and then drop this into your app project. Now, just for a minute, we'll take a look at that game, the actual. So this is, again, a HTML and JavaScript app, and it's going to have several pieces. It's got some CSS collateral. It's going to have, here you're going to see right here, the DLL that comes from the actual component that's dropped in, the WinMD for that DLL. And those two things together is what's sufficient to be able to wire this up, with the one addition that when you get into the manifest for this has been covered in several of the other sessions, the manifest for this has to have a declaration of this extension so that you can know that that's actually how the runtime will register this component and make it available to you. It's actually going to be able to activate it for this. So if we go in with the typical markup and code behind, actually, I guess I'll just open it in the, So there you can see, of course, that's the HTML version of it. But if we wanted to just, I'm going to use Notepad for this, my old days. But there's going to be the typical GUI of markup. And really what we're doing is just setting up the canvas and the SVG so that they're there, and then having just the necessary buttons to be able to manage the stuff and be able to show data as you'd seen. And the real meat of what we're going to be doing is going to be down in the JavaScript part in the game itself. And here, let's open this up in something that's a little more amenable to this code. So here, there's just basically a bunch of state. And at the lowest level, let's go down to the bottom here, and see that when the window is activated, that we're going to go in and set up what we need. And that includes the two rackets, the ball, everything all set up. And then really this is just, common to the game. And it's going to any game. And it's going to do a loop to be able to do that. So the game loop is what we really care about. And the game loop is here. And simply enough, in JavaScript, this thing is just going to run through at the interval. And it's going to check for collisions. And one of the big things that it has, here's where we finally get to the point that's relevant. And there's some things for video capture, of course. But here's where we get to the meat of things. And that is, we're going to be talking through Windows Runtime in this projection to this effect. And we get down to where we're going to do the configuration. So this is talking down and setting it all up. And then we're going to set up the actual event for the thing, where it reports that it found a spot. And then we're going to use that spot to be able to modify the locations of the paddles. So really, you can see that when we're consuming this effect that was down in C++, that it's pretty straightforward to be able to just use standard JavaScript paradigms to get at this and do some very simple math and be able to modify this to have the game work. So hopefully that was enough to show here to get a sense of it. So then, of course, the game itself just fits the standard HTML and JavaScript Metro style model. Okay, so we got a sense of that. So now we can move on a little bit to I'm just going to reinforce here what I said, is that, of course, because you're talking C++ COM, you're going to have the IDLE that's going to define that COM contract. You're going to implement under it. That's obviously just the standard patterns within COM. And then that IDLE is going to make your metadata, your WinMD. And then finally, you'll be able to package this up. I should mention here there are actually two ways right now of making an extension. And one of those is the one that existed first, which is the Windows Runtime Library version. So there's some runtime support and so basically some APIs that allow you to create an activatable class down in this C++ code. And for that, you would actually need to use Visual Studio Pro or Ultimate. There's a high-level way that came on late enough that we don't actually have the collateral available for you. This is one of the reasons, the logistics thing I was talking about, that at the high level, Visual Studio Express has a C++ template, which is for being able to do a Windows component DLL. And if you look in there, if you go into Express and you look at the pattern, or look at the templates, you will see that that component DLL there. And if you build it at that level, the key thing you're going to see is this public sealed class. And at that level, you can call into whatever is an approved API, and you can really do this at the higher level and only use Express. So there are certain cases in which the low level may be best if you're migrating code you already have and you really want to make use of a lot of COM GUI. We expect to provide further guidance around this. The samples will be updated to really show this off. The existing samples we have queued up that didn't make it because of the logistics issue are all using the low-level WRL, Windows Runtime Library, but we expect to have some collateral that shows the high-level way of doing it. I was going to show another sample, but given that I took a little more time than I planned, we actually could show it, kind of rush through it, but what this is to show is I will just talk about it only because it's not really that interesting. What it is, it's going to show a video, and it's just going to show that this effect that we have turns it into grayscale. I mean, you're probably not going to jump up and down about that. But just to say what it's doing, it's a sample that you can access at least the code for at the application level. So it is called Media Plugins. If you Bing it, I went and checked. I wanted to make sure it was there. If you Bing for Media Plugins, related to the build collateral, you will find this sample, and you can run it yourself. And actually, it's set up so that it's structured so that it has, at the highest level, like many of the samples, it has kind of a general entry point that is for scenarios of what you want to do. And some of those things are, do you want to do an effect? Do you want to do a codec? Different kinds of things. And then at the next level, once you step into that, it has actually which one of these do you want to do. And in there is like grayscale, a grayscale effect. That grayscale effect is actually the code overall from we've had in the Windows SDK from Vista and Win7. It's the MFT grayscale sample. So that's available to you online. You can access that. And of course, the completely classic one that's there, the traditional desktop one, won't have the modern activation piece, the hybrid, but as basically an exercise for the reader at the moment, you could actually add that activatable class, add that iInspectable derived interface to be able to Metro UI style or Metro style activate it. So, but I just do want to reinforce that when you consume this component, what the code is actually doing, this is pretty much straight from that code, and there's JavaScript and XAML. There's all three flavors of JavaScript and all three paradigms there available. But here, what usually happens is for an effect, the pattern that you use in the app is really that you're going to clear all your effects out. The effects are just put in order based upon you calling the insert, which is the second highlighted area. And so what you do is you clear out your effects if you don't want to have any other ones in, and you add an effect. You can add multiple effects. They'll be put in effectively in order. And so it's that simple. And because this is right on the video tag, it's not something where you're having to go through a Windows runtime namespace or extension in order to get it. It's right on the tag. So let's spend a few minutes. So here, actually, let's take a breather for a second. So we've talked to a pretty deep level about an effect and how we could use it. And now what we're going to do is go off to spend the remaining time on looking at some of these more advanced cases. And again, as I said, we'll be kind of broader and definitely not as deep, but we'll have some pointers and some ideas here. So the first thing is when we said, okay, we want to do let's say we want to do a new transport, because a media source could actually just read directly from a file. It could be doing, just straight file I/O. It doesn't even need any other help. But if we want to do something like adaptive streaming with it, then we start caring about what this thing looks like. And a media source really has two pieces to it, as I mentioned earlier. One is the transport part. So like if you want to do adaptive streaming, that piece of the two roles of the media source would be important to you. And then also there's the container parsing. That wouldn't be if you were using a standard file container for this content. So what you'll have, though, is you've got some kind of aggregate stream coming in, and then you're going to be, of course, doing what you need to do to actually do the I/O for it, and on the second half, being able to actually demultiplex it, to parse it, and turn it into elementary streams that can go into the rest of our pipeline, or even to your own decoders and such. So there, the standard interface for this from the desktop model, which is preserved, is IMF media source. That's shown up on the upper right. And it has the typical transport controls. You can get it started and do all that. And again, the one thing that's new is that green metro-style activation part of it that makes it the hybrid, so that it becomes activated that way instead of COM instantiated. And you can use the typical activatable class ID, the string within the namespace, to be able to get it put in place. So, of course, we could use this for various types of streaming. And in fact, there's efforts, if you go to Talk 776, Daniel has information about IAS and what they're going to be providing that will integrate in using these concepts. So here, just for a minute, we're going to go into, these are just the native parts that are underneath. Like, let's say we're playing back something with the video tag. And I mentioned that media engine. That is the layer that fuels the audio and video tag and the XAML media element, and also is available directly as C++ for the lowest level if you want to use it with iCore window, an iCore application. And then what happens underneath that is really overall our traditional source resolution mechanism. So here, again, what I talked about was that you may have a file extension or a MIME type. Those would be fit into what's called a byte stream handler. So effectively, you've got this indirection where you register this component, and this can be registered within the metro-style model. There's actually an API for it. So within your app, you would say, register this thing, and it's going to handle a certain format. And then what it'll do is cause a cascade to pick out another component shown in the bottom left, which is the byte stream. A byte stream is really an optional component. Like I said, you could do direct file I/O if you wanted to from a media source. But often this abstraction of a byte stream within modern OSs is very useful, that you can say, I can have a network input, I can have various other types, and a byte stream overall is going to make it so that that's really looks consistent to the system. I should point out those two left boxes are not actually part of the Media Foundation topology. They are things that lie in front of it that, again, part of source resolution, and there's some links here to learn about those. And then they cause the cascade that makes the media source be selected out of the system. That will flow through the rest of the pipeline. And really, as I said, the media engine is like a super frame server for that. And here's code just reinforcing that you actually have a Windows Runtime API, a projection that allows you to register one of these byte stream handlers and/or scheme handler. And in this case, this code is just showing being able to have an FTP protocol that actually has a foo extension that can be used for handling your own file. This is the listing of the Media Extension Manager, which you can Bing for. I made sure that it actually shows up. And you can even Bing for these individual methods, and that you can register these things within the metro-style model and be able to leverage them within your application. Again, this is purely within the application. There's no global machine-level installation or registration, and that's all part of that confidence model of the Apex package. So the sync, all I'm really going to mention here is that it's very symmetric. This thing has the multiplexer for, like you're going to put something into a new type of container. And the other aspect of it, you may not actually want to be doing that part. You may want to be outputting to a new transport, so you can use that aspect of it. There is the possibility in some cases, if you want to leverage an inbox parser or multiplexer, to use containment techniques. You could basically, like, for example, on the source, you could wrap our media source with your own component and register it local to your application, and then be able to, within the usual containment wrapper, or some people call it aggregation, to be able to leverage our component under the right conditions. Now, we're finally going to get into, if you wanted to do format support, new format X, what you get into here is this gets very complicated. Of course, codecs are highly algorithmic, even some of the simplest ones. Of course, we're not taking something like PCM, which really doesn't qualify as a codec. But historically, what we've run into is that there was sort of a wave where people thought of codecs as being, they would be completely amenable to massive parallelism. That you could use GPGPU techniques and you could do a great codec, or just really, like, say, for example, direct 3D resources. The reality is it can't be done efficiently that way. You really need to have pretty much specialized hardware to do a good codec. And you get even into the difference in efficiency that you can use an ASIC in a half a watt that can do what an entire D3D pipeline takes several watts to do. But I would mention that the graphics vendors have gone to the effort to put these specialized hardware pipelines for video into their GPUs, so that you can get the H.264 and other processing that you need there. So they've done a great effort to keep making that better, to make that acceleration more efficient and everything else. But it really requires a dedicated pipeline in general. That doesn't mean you can't use shaders, and shaders can be quite useful. But I provided some other links that MFTs, as I mentioned, at the simplest level, they're synchronous, and that's easy to do. And then what you can do is, if you want to descend into understanding more about MFTs as codecs, there's a next level. And then finally, when you do acceleration per the model that we support with GPUs, that would be DirectX video acceleration. And that has a very well-defined API and DDI down into the hardware. And the APIs for that are, of course, decoupled, unlike DirectShow, where they were coupled into the video render. They're actually decoupled in that case, and provided as just completely discrete APIs that can be leveraged. And then finally, hardware MFTs. There's the ability for cases where, in Windows 8, where we don't have support in a format for hardware acceleration ourselves, to be able to actually take an MFT as the object model that encapsulates totally arbitrary decoding or encoding that is accelerated by whatever you may want. And that's actually incredibly useful for the encode model, because DXVA doesn't have any surface area for encode. It's only for decode. So hardware MFTs really come into play for the acceleration model for encode. And then also the other aspect of handling a new format is containers. And here, for example, if you've ever cracked open like the MPEG-4 container spec, you will spend a long time because every time you're talking about a container, you're usually having complex bit fields that have variable sizes and optional elements and all these other things, and it can become a very large effort. In fact, we spent basically at least a couple of our milestones in Windows 7 with our development team getting the ISO MPEG-4 support up to what you see in Windows 7. It's quite a bit of work in order to do it in a very solid, robust fashion. So just to finally get down to it, we're really saying that you make these things once as native code, and you're using really what are the traditional object models that we already had in Windows 7, just making them hybrids. And then finally, that you'll be able to use these things with Windows Runtime as projection. In some cases, as we talked about, like audio and video tags or the XAML media element, you won't really be using Windows Runtime directly. It will all be happening for you as specific wiring, specific integration. But when you go to the other cases, like for transcoding and capture, you will actually see these things as where they make sense across all languages, Windows Runtime. And then, of course, the list of related sessions and some other links of information that you can go to. And hopefully you've found this useful, and I really appreciate you coming to this session. Okay.